Welcome back to the course. In this lecture we will learn about some of the types of graphs and some terminology used in graph theory, to have some basics before we start studying algorithms. The main two types of graphs are the indirected graph and the directed graph. You really need to understand these because you will hear about them a lot. Both of these types of graphs still follow the concept of having vertices that are connected with edges. The difference between them remains in the nature of the edges. In an undirected graph, edges don't have a particular direction. It's a two-way relationship between the two vertices. We can go from vertex A to vertex B and vice versa. An example of that is friendship in Facebook. If there is an edge between two people, it means that they're friends. Green is friend with blue and blue is friend with green. It's reciprocal. But in a directed graph, also called digraph, an edge has a particular direction. You can see that it has a tail and a head. And here, the direction matters. We can go from A to B, but we cannot go from B to A. An example of that is following on Twitter. If we have two people, green and blue, and there is an edge like this, it means that green follows blue. But the opposite isn't true here. Here, the edge has a defined direction. It goes from green to blue. So green follows blue. It's a one-way relationship. Another quick example to better understand the two types, we can mention family relationships. For example, if we have a graph where an edge represents sibling relationship, then we use an undirected graph, because if A is a sibling of B, then B is also a sibling of A. It's a two-way relationship. But if we have a graph where an edge represents father-son relationship, we use a directed graph, because it's a one-way relationship. If A is the father of B, it doesn't mean that B is the father of A. It's even impossible in this example. We also need the direction to determine who's the father and who's the son. For example, here A is the father and B the son. But if we reverse the edge, B becomes the father and A the son. Another major difference between undirected and directed graphs is in traversal. Later, when we will learn how to traverse a graph, we will see that in an undirected graph, we can jump from this vertex A to the vertex B. But we can also jump from the vertex B to the vertex A. It's permissible. However, in a directed graph, if an edge goes out from A and goes into B, we can only jump from A to B, not the other way around. It's like an arrow that shows us what direction we can take. Now that you hopefully understood undirected and directed graphs, we can move to the next types, unweighted and weighted graphs. In the previous lecture, we've talked about the example of finding the shortest path between two vertices. If you noticed, there was an integer on each edge of the graph. That integer represents the distance between two vertices. In a more general way, that value represents the weight of the edge. You've guessed it, a weighted graph is a graph where we associate a weight to each edge. That weight can represent a cost, a distance, a speed limit. It depends on the purpose of the graph. And an unweighted graph is just a graph with no weight on its edges, like the one we've seen in the car rides example. An edge simply meant that two car rides overlap. That's it. We don't need to add weight to it. Now you know undirected and directed graphs, unweighted and weighted graphs. Important point, a graph being directed or undirected is independent from being weighted or unweighted. So we have undirected unweighted graphs, undirected weighted graphs, directed unweighted graphs, and directed weighted graphs. Let's move to the next point. The first two terms that we will learn about are adjacent and incident. Two vertices are said to be adjacent if there is an edge connecting them. These two vertices A and B are adjacent. And the vertex is said to be incident to an edge if it's one of the two vertices it connects. Here there is an incidence between the vertex A and the edge, also an incidence between the vertex B and the edge. Next term, an important one, degree. The degree of a vertex is the number of edges the vertex is incident to, denoted degree of V. For example, the degree of the vertex A is 3. Here are degrees of remaining vertices to better understand. For an undirected graph, a vertex is incident to all the edges in the same way. There is no need to further definitions. But in a directed graph, the edge it has an incidence with can be going out of the vertex or going in the vertex. So, a vertex can have edges going out of it, their total number is named the out degree, and it can also have edges going in it, their total number is named the in degree. In other words, the out degree of a vertex is the number of edges that start from it, denoted deg superscript plus v, and the in degree of a vertex is the number of edges that end in it, denoted deg superscript minus v. And the degree of a vertex in a directed graph is the sum of its out degree and its in degree. Here is an example. You can see that the vertex B has 3 edges going out of it, edges that start from it. This is why its out degree is 3. And it has 1 edge going in it, 1 edge that ends in it. This is why its in degree is 1. We can say that its degree is 4, 3 plus 1. Remember that it's the sum of the out degree and the in degree. And here are out degrees and in degrees of remaining vertices. Speaking of degree, we can have vertices with a degree of 0. They're not connected with any other vertex. Such vertices are named isolated vertices. An isolated vertex is the vertex with degree 0, like the vertex I in this example. Next terms are order and size, easy ones. The order of a graph is its number of vertices, and the size of a graph is its number of edges. For example, this graph has an order of 6 and a size of 8. Next term, self-loop. A self-loop, also named loop, is an edge that connects a vertex to itself, like in this example. Question now, can we have multiple edges between the same 2 vertices? The answer is yes, but we need to do the distinction between 2 types of graphs, simple graphs and multigraphs. Simple graphs are graphs that allow neither multiple edges between the same 2 vertices nor self-loops. And multigraphs are graphs that allow multiple edges between the same 2 vertices. And for self-loops, some authors say that they're allowed and some others say that they're not. And we will usually work with simple graphs. In this course, you can assume that a graph is simple unless it's mentioned that it's a multigraph. We also have other types of graphs you should know about. First, we have the trivial graph, a graph with only one vertex and no edges. We also have the edgeless graph, a graph with any number of vertices but with 0 edges. We also have the complete graph, a graph where there is an edge between each 2 pair of vertices, denoted k subscript n, where n is the order of the graph. We also have the star graph, a graph where we have one vertex of degree n-1 and n-1 vertices of degree 1. In other words, a vertex that is connected to all other vertices, and all other vertices are connected to that vertex only. I know that you're discovering a lot of new terms quickly and it may be overwhelming, but you will still be able to have a look at them again later in case you forget something, don't worry. Another type of graph is the bipartite graph. A bipartite graph is a graph whose set of vertices can be partitioned into 2 sets of vertices such that there is no edge between 2 vertices of the same subset. For example, this graph is bipartite because if we partition vertices this way, there is no edge between any 2 vertices of V1, and same thing for V2. A real-life example is players and clubs. Let's suppose that we have players and clubs that we want to represent in a graph where an edge from A to B means that the player A played in the club B. The graph that we get is bipartite because we can partition the vertices into a subset V1 that represents players and a subset V2 that represents clubs. And we can't have an edge between vertices of V1 because a player can't play in a player. Same thing for V2, a club can't play in a club. The relationship can only be between a player and a club. A special type of bipartite graphs is complete bipartite graphs. A complete bipartite graph is a bipartite graph where every vertex of V1 is connected to every vertex of V2, like in this graph. A complete bipartite graph is denoted K subscript M N, where M is the number of vertices of V1 and N the number of vertices of V2. Next type of graphs is the regular graph. It's a graph where all vertices have the same degree, as you can see here. For directed graphs, a directed regular graph must also satisfy the condition of having the out degree equal to the in degree for each vertex. Then we have two important terms, sparse and dense. A graph is said to be sparse if its number of edges is small, much less than the total possible number of edges, like this one. And a graph is said to be dense if its number of edges is big, close to the total possible number of edges, like this one. Last two subjects we'll talk about in this lecture are terms related to subgraphs and terms related to paths and cycles. We're almost done. What if we have a graph G and we create a new graph G' by taking some vertices and some edges from G? This is what we call a subgraph. G' equal to V' E' is a subgraph of G equal VE if and only if V' is a subset of V, E' is a subset of E, and incident vertices of every edge in E' are in V'. In other words, we cannot take an edge from G without taking its two incident vertices. In math notation, it's written that if an edge UV is in the subgraph, then both U and V must be in the subgraph. For example, we cannot take the orange edge without taking 0 and 3. Two special kinds of subgraphs are spanning subgraphs and induced subgraphs. A spanning subgraph of G is a subgraph of G where we take all the vertices and possibly remove some edges. Look at the example. We took all vertices of G and removed some edges. And an induced subgraph of G is a subgraph of G where we can remove some vertices, but we take all the edges, except ones that are incident to vertices we removed obviously. So the set of edges contains all edges of E whose vertices are in the subgraph. In the example, we removed two vertices and kept all edges, except the ones that are incident to vertices we removed. And the opposite of subgraph is supergraph. If we take a graph G and add to it some vertices and or some edges, we would have created a supergraph of G. We can say that if G' is a subgraph of G, then G is a supergraph of G'. Last topic now, terms related to paths and cycles. First of all, you need to understand what is a walk. A walk is a sequence of edges that connects a sequence of vertices. Basically, you can think of it as a line that traverses vertices. Obviously, each vertex it traverses has to be adjacent to the next one. And the walk can have repeated vertices and or repeated edges. For example, in this walk we have repeated vertices J and D, and a repeated edge, the one between J and D. By repeated vertex, we mean a vertex that we pass from more than once. And same logic for edge. A repeated edge is an edge that we pass from for more than once. And we have two types of walks, open walks and closed walks. An open walk is a walk where the first vertex and the last vertex are different, like this one. And a closed walk is a walk where the first vertex is equal to the last vertex, like this one. Basically, it's a walk that goes back to where it started. Now you know about walks, you still need to know about trails, circuits, paths, and cycles. A trail is simply a walk that doesn't allow repeated edges. For example, this one is a trail, this one is a trail, but this one is not. It contains a repeated edge, the one between J and D. A circuit is simply a closed trail, a trail whose the first and the last vertices are equal, like this one. And a path is a walk that doesn't allow repeated edges but also vertices this time. For example, this one is a path, this one is not a path because it has a repeated vertex, and same thing for this one, not a path. We also have the concept of cycle, very important. A cycle is a closed path, a path where the first and last vertex are the same. Even if it doesn't respect the condition of having no repeated vertices, but an exception is made for the first and last vertex. So a cycle is a walk with no repeated edges, no repeated vertices, except for the first and last one. The definitions we've seen now also have the directed version. For directed graphs, we have directed walk, directed closed walk, directed trail, directed circuit, directed path, and directed cycle. The difference is that we have to respect the direction of the edges. For example, this one is a directed path because all edges are in the same direction, but this one is not, because of this edge. Even if vertices are adjacent, but the direction isn't respected. Basically, each ending vertex of an edge must be the starting vertex of the next edge. And from definitions we've seen now, we discovered two new types of graphs, cyclic and acyclic graphs. An undirected cyclic graph is an undirected graph that contains a cycle, like this one. One of its cycles is the orange one. And obviously, an undirected acyclic graph is an undirected graph that doesn't contain a cycle, like this one. For directed graphs, a directed cyclic graph is a directed graph that contains a directed cycle, like this one. An example of a cycle inside it is the one in orange. And a directed acyclic graph, DAG, is a directed graph that doesn't contain a directed cycle, like this one. Last three terms, reachable, connected, and disconnected. We say that a vertex B is reachable from a vertex A if there exists a path from A to B. For example, here we can go from A to B, so B is reachable from A. For connected, we say that a graph is connected if there exists a path between every pair of vertices, which is the case in this one. But for this one, for example, we don't have a path between A and E, hence the graph is not connected. We say that it's disconnected. This one is for undirected graph, because for directed graphs, we have weakly connected and strongly connected. Weakly connected graph means that there exists an undirected path from each vertex to each vertex. An undirected path is a path that doesn't take edges direction into consideration. In other words, if we remove edges direction, we get a connected undirected graph. And for strongly connected, there must be a directed path from each vertex to each vertex. Here we take edges direction into consideration. For example, this graph is weakly connected, but not strongly connected, because there is no directed path from A to C. But this one is strongly connected. We have a directed path from any vertex to any vertex. And we finished this lecture where we introduced a lot of terms and types of graphs. I know that you had to understand a ton of new concepts quickly and that this lecture wasn't that fun, but as said earlier, you will be able to go back to them again later if you forget something. Also, You will have a quiz where you will be able to evaluate yourself and see if you understood what we talked about in this lecture. Okay, now we know what is a graph, some of its types, but an important question comes in mind. How is a graph represented in the memory of our computer? This is what we will talk about in our next lecture. I hope that you understood this one, and see you in the next lecture.